A very pleasant good morning to one and all present here. Research is to see what everyone else has seen and think what nobody has thought. I hereby welcome you all to the second day of two-day international conference on recent trends and hurdles in physical sciences research. We are now living in the world where we observe the rise of many and many research institutes, not only in India but all around the world. Let me explain the importance of research. The main aim of research is to bring out the universal truths that are present around us. Research also brings us a better understanding about all matters present around us. It also enhances new ideas and benefits human lifestyle by developing the present technologies. Commemorating the Almighty brings out the light in every success. Let's start our day through a prayer.
Oh Lord my God, when I'm in awesome wonder, consider all the worlds thy hands have made. I see the stars, I hear the rolling thunder, thy power throughout the universe displayed. Then sings my soul, my Savior God, to thee. How great thou art, how great thou art. Then sings my soul, my Savior God, to thee. How great thou art, how great thou art, how great thou art, how great thou art.
Now, let me welcome Ms. Abhayavi Shankar, Assistant Professor, Department of Physics, to welcome speech. Please, ma'am.
Thank you, Amrita. With good morning, all. With immense pleasure, I welcome you all to the second day of International Conference on Recent Trends and Hurdles in Physical Sciences Research, organized by Department of Physics in association with IQAC, Chrysler College. Today, in the forenoon session, we have invited lectures by Dr. Harikrishnan S. Nair, Assistant Professor, Department of Physics, University of Texas, Dr. I. Hubert Joe, Professor, Department of Physics, University of Kerala, and Dr. Sunish Mathews, Research Associate, Center for International and Surgical Sciences, University College, London, UK. In the afternoon, we shall continue with the paper presentation session, which will be chaired by Dr. N. Ponpandian, Professor and Head, Department of Physics, Bharatiyar University. Despite their busy schedule, our beloved guests have accepted our invitation to join the conference. We are truly fortunate to have such eminent personalities and distinguished minds here with us today. Once again, I welcome all our beloved guests and participants on behalf of Department of Physics, Chrysler College, Maranellu, to the second day of our international conference. Thank you.
Thank you, Abhaya ma'am. It's my privilege to invite Dr. Harikrishnan S. Nair to the session. Dr. Harikrishnan is currently working as an assistant professor in the University of Texas, El Paso in USA. He did his PhD in condensed matter physics from Indian Institute of Science Center, Bangalore. After PhD, he was a postdoctoral researcher at Forskningscentrum Jülich GmbH University of Johannesburg and Colorado State University in US before joining UTEP as an assistant professor in 2017. He was nominated for Alfred P. Sloan Research Fellowship and was an invited speaker at Quantum Materials Young Investigator Workshop at Oak Ridge National Lab. I'm handing over the session to you, sir.
Can you hear me and can you see the screen? If I can go ahead and share the screen. Can you hear me?
We can hear you.
And you can see the slides?
Yeah, of course.
Okay, all right. So no, thank you very much for this, for the introduction, for the invitation. So today's talk, I want to present something related to the work that I've been doing for the past few years, which is looking at certain specific lattices of honeycomb lattices of certain transition metal elements. There is a specific interest in looking at these systems from the angle of quantum computing on the one hand. On the other hand, there is interest in looking at these systems from a fundamental point of view, from a fundamental point of physics condensed matter research, which has got to do with the kind of magnetic phases that these systems can realize. So I'll shortly explain what that means. And the particular compound that I will present some results on is called a barium cobalt phosphate, and there's a specific structure of that compound. It's a gamma phase, meaning that the compound can have many different structural phases, and we are looking at one of them. So that motivates the title of the talk. It's about the quantum magnetism as seen in certain type of honeycomb lattices. And as an example of that, I will present something on this specific material, barium cobalt 2 phosphate. So this is the research. There have been a bunch of people who contributed towards this work. The prominent ones, the names of prominent ones are flashed on the screen. So I'll start by giving a rather a detailed introduction of what these materials are and what's the interest in, so that it might be more interesting and engaging to understand. Now, the entirety of this type of research, most of quantum magnetism and complex magnetic materials that is happening in condensed matter research has got to do with what is known as emergent phenomena in materials. So if you look at the slide on the left-hand side, you can see that it's written examples of emergent phenomena. So then it remains to explain what emergent phenomena means. So you can look at the slide. It's an arrow from hydrogen onto other materials which are more complex than hydrogen. So as the arrow goes from left-hand side to the right-hand side, you will see that it's indicating hydrogen, niobium, gallium arsenide, alloys, and cuprate perovskites. So it's an arrow that indicates an increasing degree of complexity as you move from the left to the right. So on the left, you have simple atomic physics. So if you want to try to understand hydrogen, you would probably do a very basic quantum mechanical approach. You would write down the wave functions, you can solve them, and you can explain what are the properties. You can write down the ground state, you can find out the energy of that ground state, things like that. It's pretty simple. And you would explain that based on the building blocks, which are electrons and protons and neutrons and such. So it belongs to a category of materials where you can explain everything based on the components present in that system. So that is what we would call a reductionist approach, so that you know the sum of all these would explain the total material that is there. But then as technology progressed, we started to discover new and complex materials, which are not just one element, but a mixture of many. So if you look at cuprate perovskites, there are many materials many elements mixed together. So you would have copper, you would have oxygen, you would have strontium, you would have many other elements which are mixed together and made into a very complex system. Now, what happens in this system is that all of a sudden you see properties like superconductivity, for example. You make a compound containing 3 or 4 elements and you suddenly discover superconductivity. Why is it interesting? It is interesting because none of the elements that you mix together may not be or need not be superconducting. Copper in itself need not be superconducting, but then you can mix them together in various ratios, and you can have a property emerging from that, which was not present in the constituents. This is loosely the importance of emergent phenomena, that you start to see properties which are not present initially in the ingredients. So we are at a point where we are seeing very many new phases of matter being discovered in solid materials. So superconductivity is very well-known example. Multiferrocity is another thing. Quantum spin liquids is yet another thing. Any type of new excitations, any type of new particle excitations found in a solid is a new type of magnetic phase, a magnetic ground state, and a resulting excitation that belongs to this category. So then what is so important about this applied to a magnetic material? So in order to explain that, we need to look at something which is very simple, a very simple unit of spins arranged on a lattice. So I show you a triangular lattice. It just means that there are 3 atoms on the corners of a triangle. So that is what I would call the basic unit of this lattice. And then this would expand in ad infinitum to make up the whole crystal structure. So if you're assume that you are looking at a very tiny corner of a big crystal, and then you can see the atoms. Let's assume that you can see the atoms, and you are looking at 3 of them, which arrange in such a way that they are at the corners of a triangle. And then you have spins, which are magnetic moments, which are arranged on the corners of the atoms, of these 3 atoms. Now we impose a constraint that they have a ferromagnetic interaction between each pair, and assume that this is a condition which tells each of these red arrows that they should point in the same direction. as its neighbor. So you look at number 1, the arrow is pointing up, and then you look at number 2, which is its neighbor, the arrow is also pointing up. So the neighbors the arrows are pointing up. That is the ferromagnetic interaction that I'm talking about. This is a loose statement, but that would help you understand it. Now you look at 1 and 3, which is another neighbor of 1, the arrows are still pointing up. Now you look at 2 and 3, it still holds the same. So this type of arrangement of spins is called an icing spin. So it would point either up. At the same time, you're not violating any rule if these arrows are pointing down. So in other words, you can have only 2 states. You can name it plus or minus or 1 or 2, but the states are just that the arrows are pointing up or they are pointing down. So that gives you a 2-state system, meaning that it has 2 ground states. One in which all the arrows are pointing to the north, and the other, all the arrows are pointing to the south. This is a special condition when there is ferromagnetic interaction between each pair. Now what happens if you have, so these are the 2 states. You can have, on the left-hand side, you can have all of them pointing up, on the right-hand side, all of them down. And this is a completely fixed, stable state, and you call it doubly degenerate. So if you have done quantum mechanics, you would know about degeneracy, that it is equal in energy. So they have equal energy ground state, and they are degenerate. So the system would fluctuate between these 2 states. Now what happens when you relax this, and when you have real systems, you can have very many ordered ground states. So you can have diamagnets, you can have paramagnets, you can have ferromagnets, antiferromagnets, and so on and so forth. So these are different ground states, just like this one. This is a ferromagnetic ground state. You can have very many other ground states, but these are all known as ordered ground state. Why ordered? Because they have a perfect order. On the other hand, they also break the symmetry. So if they're pointing in random direction, there is no symmetry breaking. But then when they start to order, they break the symmetry of the space, meaning that now it's not isotropic. If you look at different directions, you would see different arrows pointing in different directions. So you break the symmetry when ordering starts to happen. And then there would be an order parameter for the transition that is happening. So we will come to that part later, but then it's enough to understand at this point that you can have many ground states, and some of them, like we discussed in the ferromagnetic interaction, you will have an ordered ground state. And yet there will be degeneracy. So that is for this particular case. Now let's look at something slightly different. The same system, the same triangular lattice, but then you have antiferromagnetic interaction. Now what is that interaction? It just means that instead of having the neighbors pointing in the same direction, you want the neighbors to point opposite. If one of them is pointing to the north, you want the neighbor to point to the south. Now, all of a sudden, in the previous case, you had only 2 degenerate states because all of them were pointing up or all of them were pointing down. This is when there was ferromagnetic interaction. Now you relax that and you change that to AFM interaction, meaning antiferromagnetic interaction. And all of a sudden that 2 ground state explodes into 6 ground states, just for 3 spins with antiferromagnetic interaction. So you would have, you see in the diagram here, you have triangles with a red arrow point, a red line. So the red line indicates that you have the ferromagnetic kind of arrangement there, but it's because it's not able to accommodate all the interactions at the same time. So if you look at any one of them, you will see that two arrows are pointing opposite. Two pairs of arrows are pointing opposite, but then there is always one pair which is pointing like the previous example. And that pair is indicated by a red line. So the system is unable to satisfy the constraint that we have applied, that every neighbor must point opposite. It's not able to satisfy that. So it would, what does it do? Instead of 2 ground state, it would expand into 6 ground state, and it would start to fluctuate between these 6 ground states. So all these 6 ground states are of equal energy. Now remember, all I have shown is just 3 atoms on a triangular lattice. Now, if you look at a macroscopic crystal, you will have 10 to the power of 23 kind of atoms involved. So when you take a real material, you have classically large number of degenerate ground states available. What is the result of this degeneracy? It means that you will inhibit the formation of an ordered ground state. You will no more have an ordered ground state like these, like a ferromagnet or an antiferromagnet or a ferrimagnet or a paramagnet. This is no longer possible. Why? Because the system keeps fluctuating between a large number of available degenerate ground states. This is a very important concept. This has a very important consequence in the magnetic properties and observation of physical phenomena in magnets. What does it do? It actually gives rise to novel ground states which we have not encountered before. Now, there are ways to look at these systems through simple experiments, and then one can ask, does this happen only if you arrange atoms on a triangle? The answer is no. It can happen in a large variety of systems. And there are certain classes known as frustrated magnets where this can happen so easily. So it has got to do with the geometry of the lattice or the space of the lattice. Just like any triangle, which is the example that I have used, you can arrange triangles in another fashion, and one of them is called a kagome. So that's the second from the left figure that you see here. And these two can be thought of as two-dimensional, meaning that it's an arrangement on a sheet of paper, on a piece of two-dimensional plane. You can go higher in dimension. You can go to 3 dimension, and in 3 dimensions you can have tetrahedras arranged like it is shown on third figure, which is called a pyrochlore. These are minerals that we know, like pyrochlores are minerals that we know that can be found in the nature. Another 3-dimensional arrangement is the diamond structure. So the diamond structure is also something that we know from nature. Minerals adopt it. And it's a particular arrangement like it is shown here in the left bottom figure. Now, for the sake of this talk or this particular work, we focus on a 2-dimensional arrangement called honeycomb. Now, you can see that's the last figure on the slide towards the right bottom. And I have indicated atoms on a honeycomb structure with 2 different colors, red and blue. And there is a reason for it. The reason is that the surroundings you see when you are at the blue atom is different from how it looks when you are at the red atom. So that's a reason. So it looks slightly different. You can compare that to the triangular net, where if you are at any of the blue atoms, the surrounding would look the same. So there is a specific name for these things, but then it's not important. What is important is to understand that the surroundings of a honeycomb is different when you are located at any of the 2 atoms than you are in the triangular lattice, for example. All right, so why is the honeycomb so important, and what exactly in honeycomb? So we started the talk by showing you a triangular lattice, and we imposed a constraint. So the first thing was the geometry of the lattice. The second thing was a constraint. So the first thing that I said is about the lattice. Here, it's a honeycomb. Now, what is the constraint? The constraint here is called a Kitaev model. And what does that say? It tells you that any interaction between the spins on a given honeycomb. So you can look at the central honeycomb with the markings 1, 2, 3, 4, 5, 6. So any interaction will have to be along the bond, which means it has to be along the line that connects the atoms, not anywhere else. So that is the constraint, and each of that constraint along the bond that connecting the atoms is called an interaction. So there are 3 of them, because there is one along X, one along Y, and one along Z for the honeycomb. So it's color coded. You can see it as a blue, red, and green lines. So it's a 2-dimensional model, meaning that atoms are arranged in a plane. There is no height. It's only in the plane. And it is exactly solvable, meaning that you can solve it using pen and paper. You don't need a computer to solve it. Not exactly, but you don't need to do a computation to solve it. Now, why is it interesting? It leads to something called an excitation or a particle or a new particle called Majorana fermion. So it's like a fermion. So one of the fermions that we all know is the electron, or a boson like a phonon. So these are particles that we know from textbooks, from Fermi-Dirac statistics and Bose-Einstein statistics and things like that. This lattice gives rise to a new type of particle, which is called Majorana fermions. And why is it important? What is so big about Majorana fermions? The important aspect is that they can be used to store information. In other words, they can be used for quantum computing. So that is the interest. And how so? Here is how it is. So you know that bosons and fermions are described by wave functions. You can interchange bosons and fermions, and then there is a complete statistics that follows from it. And it depends on how you interchange a boson and a fermion. If you interchange fermions, then you incur a phase factor of -1. And for bosons, it is +1. So you can safely interchange them. And as a result, you can have more than one bosons in one state, but then you cannot have that with fermions, and hence you have the exclusion principle, the Pauli exclusion principle. Now there are particles intermediate for that, or in fact a superset of that. These are called anions. And these materials, these quasi-particles, these particles can take any value between 1 and -1 for the phase factor. So the Majorana fermion is one such, and they obey a very different statistics from Fermi-Dirac or Bose-Einstein. They have a separate statistics. Are these particles really existing? They are. It's very recently people have found these kind of particles exist in a real lattice, and they found out their statistics obey what is known as a fractional statistics. What is so interesting about fractional statistics? Well, it actually in the late 70s, it even won a Nobel Prize for what is known as quantum Hall effect. A quantum Hall effect, I mean, that Nobel result is the graph that you see on the right hand side. So if you apply a magnetic field and measure the transverse resistivity of some of these thin films, people found that there are plateaus, there are regions where the graph is like plateauing. And then that happens at fractional values of electrons. So nobody could think why an electron would, a quasi-particle can exist in a material, yet have a charge which is 1/3 of an electron. How can you have something 1/3 of an electron? The reason is that it's a quasi-particle. So this is what you call a fractional quantum Hall effect. And it's a topological property, and that can be used for quantum computing. And that's the interest. So if some of the thin films can show quantum Hall effect, if similar particles exist in honeycomb lattice based materials, can we use that for quantum computing? That's the interest. And there have been some work in the past. It's not all brand new. And people have looked at similar honeycomb systems, but not exactly honeycomb, in Kagome lattice antiferromagnets. So people have looked for fractional excitations. What are fractional excitations? It's nothing but quasi-particle excitations that can only be accounted for if you assume that it's a fraction of a fundamental charge or a fundamental property, which you think cannot be fractionalized, like electronic charge, for example. So one of the recent system is a honeycomb system, and that is why there is an interest, and that interest is promoted by what is known as spin liquid ground state and emergence of a Majorana fermion from the ground state. So if you have a honeycomb lattice, and if you satisfy certain constraints on how spins arrange on these systems, you can get some type of excitation which is very novel. So that's the whole idea. So the important keywords for this you take home are fractionalization and quantum spin liquid. So it means that you can have a quasi-particle system that cannot be constructed from the elementary constituents, like from electronic charge, for example. You have to take maybe 1/3 of electronic charge, or 1/5 or 2/5, things like that. And that can exist if the ground state is a quantum spin liquid, which is an unusual phase of matter when quantum spins do not completely order. There is only long-range quantum entanglement of spins, but there is no long-range magnetic order. There is no ordinary magnetic order. So those are the two important ingredients to what we are looking at. So now into the crux of the matter, we want to look at this honeycomb lattice, and we want to look at a honeycomb lattice with a specific spin populated on that lattice. So we chose cobalt-2 plus. Why? Because there is a very specific energy level diagram for cobalt-2 plus, such that it can be approximated as an effective spin half system. So cobalt-2 plus has 3/2 as its spin. This is computed from the Aufbau principle and Hund's rule and things like that, which you learn in quantum chemistry. So you would just arrange the electrons as per the energy level goes, and then you just add them up. But then here, there is something else called a crystal field that comes into picture and causes some kind of splitting. So this is like Stark effect. If you have an energy level in an electric field, you would say that the energy level would split up. So these red lines on the right-hand side are those energy levels that got split up. And as a result, you see the last red line is far removed from the next one in energy. So there is a larger gap. And hence, the interaction between those two is minimal. So why is that interesting? It's interesting that you can approximate that ground state as a pseudo spin half. So remember, when we introduced the Kitaev model, or when we started this talk, we said we are looking at spin half systems. So here, it's not exactly spin half, but it's a pseudo spin half. It's an effective spin half. So that is the reason for taking cobalt 2+ in this case. Now, this system in general, when you have honeycombs, you may not have the Kitaev type interactions along the bond. If you look here, it's all these red dots are magnetic moments or spins or atoms carrying spins. And all the lines that you see are the interactions. So the interactions are not along the bonds, but it can be just across the atoms. So diagonal to sorry, diagonal to the honeycombs. So those letters J1, J2, J3 stands for some sort of energy that exists between these spins such that they will align them ferromagnetically or antiferromagnetically. So these kind of systems have been studied, and it is shown that they can have a spin liquid ground state, slightly different from the type of spin liquids that we are looking at, that we want, that we desire, but yet very close. Now, if you look at the quantum version of this, it is seen that it can have two different types of ground state, depending upon if the interactions are ferromagnetic or if the interactions are antiferromagnetic. So remember, in the beginning of the talk, we looked at triangles, and we said if it is ferromagnetic, it will have 2 ground states, and if it is antiferromagnetic, it will have 6. So very similar approach here, but then on honeycombs. And then what you see here, so if you focus on one of the phase diagrams, either ferromagnetic or antiferromagnetic, it just tells you that what type of arrangements of spins on the honeycomb can happen if you change the energy values of J1, J2, and J3. So sometimes if you tune these energies, all the spins can point in one way, or some of them can point as spirals, or they can be antiferromagnetic, things like that. So that is what a phase diagram will tell you, that if I tune J1, J2, J3, they are all energies. They are all certain amount of electron volts. Okay, a few electrons, for example, or a few kelvins, for that matter. So if you change those, how does the spins arrange? What kind of arrangement do you get? That's what this diagram tells you. So we wanted to verify that on this particular compound. Then the first thing is to prepare the compound. So you have to do a little bit of chemistry to prepare them. And this was prepared using what is known as a hydrothermal method. And you start with certain precursor chemicals. You mix them together in high pressure and high temperature. And you get these very tiny crystal pieces. So you can already see that some of them has a hexagonal shape. So it's actually the shape of the lattice that the crystal adopts. Once you get the crystal, you want to look at the structure, and then you want to look at how the atoms are arranged. One method is to shine X-rays and look at the diffraction data. And literature on this material says that it can have many different phases, many different structural phases, meaning that many different ways of arranging the atoms in space. So you can have, so 3 of them are shown here, and they have 3 different space groups. We are interested in the third one, which is called the gamma phase. The other phases are not interesting because they have a very different structure than the gamma phase. It is in the gamma phase that we get the 2-dimensional honeycomb layers. That's why we picked that phase. Now we study the crystal structure using X-rays. You can look at where the atoms are, and then you can try to find out the distance between the atoms. And you can ascertain if the cobalt distances are a specific value and make sure that they form a honeycomb lattice. That's the first thing that we do. Once that is decided, you can probe further and see if there are distortions. So for example, if you have honeycomb, so this is on the left-hand side, you can see a three-dimensional view of the crystal structure. And what you see in purple are the honeycomb lattices. And they are separated by other atoms. So you have a three-dimensional structure made by two-dimensional layers of cobalt honeycombs. So if you look further using high-resolution X-rays, you see that those X-ray peaks at the top, you can see at the bottom that the base of the X-ray diffraction peak are getting broader and broader. The reason for that is structural disorder, and one main reason is they are layered structures, so they tend to distort very easily. So that's a reason for that broadening. Now, once we have the material and we have the chemical compound and we have studied the structure, we want to study further the magnetic properties. Why? Because we want to know if it completely orders magnetically or if it doesn't order. So what we want to see is that they do not enter into a completely magnetically ordered state. So how do you do that? We do that by magnetometry. We do that by measuring the magnetic susceptibility. Once you measure that, we see a very broad peak at below 10 Kelvin. And then further, it's with the magnetic field, you see that the peak would go away and it would slightly increase. So it means that there is a very broad transition. So it could be long range ordered or it could be short range ordered, meaning that it could be completely ordered or it could be somewhere in between. But what we see is that it looks like there are two phase transitions, one at 3.5 Kelvin and one somewhere around 5 Kelvin. They are nearby, but they are all in the low temperature. It becomes further clear when you look at specific heat. That means you look at how this compound would conduct heat. If you give heat, how does it conduct? So we see two transitions again here at the same time, same kind of temperature, 6 Kelvin and 3.5 Kelvin. Now comes the main part. We want to study it using neutron scattering. So we do that to understand how the magnetic entities, the spins, behave. There are two types. We do elastic scattering and inelastic scattering. The first one is done to find out the magnetic structure, the static magnetic structure. And the second one is done to find out what is the excitation. So the first one would tell you how the ground state looks like, and the second one would tell you what excitations are there. So when you do the diffraction, we find that it actually has two types of ordering instead of a single ordering. Inside this material, cobalt spins will adopt two types of ordering. One is a collinear ordering, meaning that all the spins would point along a line. The other one is helical, meaning that there is an ordering which looks like a helix. So you can analyze this data to find out what is the pitch of that helical order, or what is the periodicity of that, and what is the periodicity of the collinear order. This can be done using a data that is shown here, which is a neutron diffraction pattern. We do that, and then we find that the two types of ordering are indeed present, and their ordering wave vectors can be found out. So this is just like a vector analysis, the vector that we talk about in vector analysis. But then this vector pertains to the magnetic moment of this of this system, of this magnet, a cobalt 2+ magnet arranged in space. So we see that there are two of them, and it is understood from how the diffraction pattern changes as a function of temperature. So we identify that in the case of helical, you can look at the curves, you don't see a peak until 3.7 Kelvin. That's a red line. So the red line is also very broad. When the temperature goes below that, all of a sudden you see a peak, which is increasing, the blue and the orange. And that is the helical order that happens at lower temperature. Then you have on the other right-hand side, you have the collinear order that actually sets in by about 5.7 Kelvin. So you see the green line has already started to show a peak. And then as you go below 5.7 Kelvin to 4.7, 3.7, 2.7, and 1.7, the peak actually builds up pretty significantly. So these are the two orders. How do they look like? They look like this. So it's a honeycomb, and the red arrows are the cobalt spins, and they arrange in collinear order on the left-hand side. So it's all along a line. They are so on the left hand, so if you look at it, it's like one line of arrows pointing up, the next line pointing down, then again pointing up, if you look along the a-axis. That's the collinear order. And then on the right-hand side, you would have completely helical order. So that's completely, it's a helix. It's a non-collinear order. It's not along a line, but it's in the plane. So this compound has two magnetic domains, and these two domains coexist. Now, what can we say about the excitation? For the excitations, you have to do inelastic neutron scattering, because you have to see how much energy is transferred to the system and then find out what are those excitations within the system. So you have to do an inelastic neutron scattering. And it is through this method, this experiment, that you would probe the quasi-particle. So if there is a quasi-particle like a Majorana fermion, you should be able to understand that through inelastic neutron scattering. Now, when you do that, you see patterns like this. So each one of that pattern is at, so if you look at the top row, you will find 4 figures at 4 different temperatures for a particular incoming energy of neutrons at 3.7 MeV. Now you will see a significantly, a conspicuous red line, a horizontal line. That is at 0 energy. If you look at the axis, you will see that that's at 0 energy. That is the elastic scattering. So it's the neutrons which are scattered without a change in energy. Then you will see that there are, there is a red intensity is the high intensity. Blue is low intensity and red is high intensity. And you will see that there is some kind of red intensity that is building up at energy around 1 to 2 MeV on the left-hand side at 1.7 Kelvin. These are the excitations that we are talking about. So these excitations actually form below 4 Kelvin. And then we look at very high energy neutrons. You can see that that energy excitation actually becomes broader and broader, and it would start to spread. That is in the panel below, in panel B on the left-hand side. That's what you see. Now, there are ways of analyzing this data, and we have done it quite a bit. What we have found is the following. We have found that there are 2 energy levels or energy bands that we can distinguish. So if you look at panel A on the top at 1.7, you see 2 major peaks starting from the red part in the graph. Those are the 2 energy levels. So it corresponds to about 1.2 MeV and like 1.8 MeV or something. So there are 2 energy bands that exist in the system. And then when you have 14.9 MeV, you would have very weak intensity coming even up to 8 MeV. And the two red bands on the panel A actually merge into one. Here you can show there is a white line. If you can see that, that's how it is merged into one. So those energy bands are actually the energy bands of the excitation that we are talking about. Now there are ways of analyzing that by simulating what type of excitation can form if you assume certain energy dependent Hamiltonian for this honeycomb. And that is what we have done in this, that the result shown in this slide is actually after linear spin wave theory analysis. And you see here in at the bottom, we have taken J1, J2, J3, specific values, energy values for those exchanges. This is precisely the constraints that we were talking about in the first few slides. If we have these energies as the constraints for the spins arranged on a honeycomb, what type of ground state and excitation do we get? This can be calculated. So you have to use a little bit of computer coding for that, and then it will give you the simulated neutron scattering pattern. And that's what is shown here, such that you can compare this figure with this one, which is the experiment. So this is the experiment, this is the theory, and then you can compare both and then say where exactly and what type of phase your compound would form. So we have done this much for this compound, and we are in the process of analyzing that further to understand the quantum nature of that excitation. So what have we understood? We have understood that this compound is highly frustrated, which is very good because it can realize the quantum computing potential for it. But there are two magnetic transitions at very low temperatures. And it is because there is a collinear order and there is a helical order. So it's actually the ground state consists of two different phases. So phase 5 and phase 3 actually coexist. So it's like a mixed thing. So it's like what do you call it? It's like a salt solution. So you have two different things. You have a mixture of magnetic phases. And then it fits more towards the J1, J2, J3 model rather than the Kitaev model that we have introduced in the beginning. So it's actually not exactly the suitable material, but it looks like it's very close. And then if we can tune the J values, we can get it to a very highly frustrated system suitable for observation of novel excitations. So that's the bottom line, and that's the final set of results that we have. And I guess I have reached the end of the talk, and all the preliminary results are published a few years ago on this system. And this is all I have for today. Thank you.
Thank you, sir. It was a great pleasure listening to your valuable insights on the topic. Now, the session is open to questions. You can either use raise hand option or put your questions in the chat box. Thank you. No questions. Let us move on to the next session.
Now, I would like to invite Dr. I. Hubert Joe, Professor, Department of Physics, University of Kerala, Kairivata. He pursued his PG at Bharatidasan University, Tiruchirappalli, Tamil Nadu, and took PhD from University of Kerala. From then, he has accomplished 270 researches. He owns 17 PhDs and 107 citations. He is mainly expertised in nonlinear optical materials, DFT computations, and vibrational spectroscopy. He is the person with highest H index in University of Kerala. He has received many elite honors and awards like Mid-Career Award from UGC in 2021, Major Research Project from Defense and Development Organization 2015, Major Research Project from Council of Scientific and Industrial Research in 2013, Major Research Project from University Grants Commission in 2011, and Responder Project Department of Space from Government of India in 2007. I now hand over the session to Dr. I. Hubert Joe. Over to you, sir.
Morning. Am I audible? Am I audible? Hello? Hello?
Yes, sir, you are audible.
Yes, yes, okay. Okay. Morning. Morning. Thank you for the nice introduction. Thank you. So I'm very happy this morning for inviting me to deliver a talk, conference. Manager, principal, and the head of the department and all other faculty members. Good morning to you all. Thank you very much for giving me the opportunity. My topic today is recent trends in Raman spectroscopy. You know that everybody Sir Chandrasekhara Venkat Raman was born in Tiruchirappalli. He's an Indian-born scientist, won the Nobel Prize. He was from Tamil Nadu, gold medal in physics, 1907. Did the MSc in Madras Christian College. Sorry, Alma Mater, Madras Presidency College, Madras. First Indian Nobel Prize in 1930. Bharat Ratna Award in 1954. Lenin Peace Prize in 1957. Okay. Now, Raman discovered Raman effects, the instrument. So Raman used this instrument for discovering the Raman effects. So Raman used sun as the source, eye as the detector. So very simple instrument is used to discover such a great effect. So after that, we know that Raman spectroscopy is a vibrational spectroscopic technique. So molecules have different energy levels. So rotational energy, vibrational energy, electron energy, that everything knows, you know. So here, within the electronic level, there are a number of vibration level. Okay. So within the vibration level, there are a number of rotation level. So vibrational level transition corresponds to vibration spectra. We know that rotational energy transition corresponds to rotational spectra. So here we are considering the vibrational spectra. So this spectra will be below the first excited electronic level. That I'll explain later. Okay. You know, Raman, this was the Raman effect or inelastic light scattering is theoretically predicted by the Smagel the year 1923. The year 1928, Raman discovered that small changes occur the frequency of a small portion of light scattered by a molecule. The changes reflect the vibrational properties of the molecule. So Raman was awarded Nobel Prize in the year, say, 1930 for his discovery. No, the main hurdles is for the first 12 years after his discovery, only 1,800 research papers were published, and about 2,500 chemical compounds. Only about 12 very long years, very Why years of total years only 1,800 research papers are published. The main hurdle is the source. So after the sun source, they used a mercury light source. Using a notch filter, they have separated light, a violet light and green light. So that source is normally used. The problem is, since the brightness available per unit area is very small, you need a large quantity of the sample is required. Not only that, you have to give a say even hours, say 1 hour or 2 hours or 3 hours time to expose the sample to the radiation. So then only you'll get the Raman signal, because the Raman signals are very weak signal. It is very difficult to get it. So your first thing is a large quantity of sample is required. And the second thing is the time taken by taking the spectra is very, very long. Even 1 day will take one spectra, because we have to expose the sample for a long time to get the Raman signal. That's the main hurdle last before that. Okay. So after the discovery of laser, so in the year, that the Professor Charlestown discovered laser. So after the main features of the laser is a highly intense, highly coherent, low divergence, low line width. Okay. Since the line width is very small, high intensity, so the line width is very small, a small quantity of the sample is enough to record the Raman spectra. Not only that, since it is a high intensity, highly coherent, say the time, exposure time, the intensity, the signal is also high. Since the intensity is high, so you'll get the good Raman spectra. So after the discovery of laser, enormous number of compounds have been recorded. So many papers have been published. So now there are so many lasers, argon laser 488 nanometer, 14.5 nanometer, argon laser, krypton laser 530.9 nanometer, 647.1 nanometer. Then helium analysis, so many lasers are there. So after the discovery of laser, Raman spectra, because the name has been changed in laser Raman. The spectrometer name becomes changed is laser Raman spectrometer. Once the discovery of laser, Raman spectra has been used for all investigation, for all compounds. So many applications are there. Okay, are published. Then, I just explained what is a Raman effect. When an electromagnetic interaction interacts with the molecule, there are so many properties. The physical laws may be reflected, it may be transmitted, it may be some property like may be absorbed, some may be scattering. So many students may ask, so what is the difference between reflection, scattering? So scattering is nothing but absorption and emission. So absorption of one photon and emission of another photon. It is a 2-photon process. So scattering is a 2-photon process. Even a Rayleigh scattering, the frequencies are same, but it is a 2-photon process. Absorption of one photon and emission of another photon. Now, we know that when photons strike a solid or collection of molecules, most of them are scattered elastically. We call it as Rayleigh scattering. Rayleigh scattering or elastic scattering. Suppose if 1,000 photons incident on the molecule, 1 photon will be scattered elastically. If 10 to the power 6 photon incident on the molecule, 1 photon will be scattered inelastically with the frequency lower than the incident frequency. If 10 to the power 9 photons incident on the molecule, 1 photon will be scattered inelastically with a frequency higher than the incident frequency. See why I am just quantifying the photon means I already told you Raman signals are weak signals. That means that suppose 1,000 photons will be scattered elastically. So that means the signals are weak. if 10 to the power 6 photons in the molecule, one photon will be inelastically with the frequency lower than the incident frequency. We used to say that the frequency same as the incident frequency is called Rayleigh line. The frequency lower than the incident frequency is called Stokes line. The frequency higher than the incident frequency is called anti-Stokes line. So we know Rayleigh line is elastic. Rayleigh scattering is an elastic scattering, whereas Raman scattering is inelastic scattering. Now, so, you know, this is just I would like to say this is Rayleigh line. Rayleigh line, the intensity is high. Right side, the frequency is higher. So this is anti-Stokes line. This is the frequency is lower. This is frequency is lower. This is Stokes line. So the Stokes line, left side is a Stokes line, right side is a anti-Stokes line. So central is a just you see the intensity. Just visualize the spectra. Central portion is a high intensity signal. Left side is a intensity lower than the Rayleigh line. Right side the intensity lower than the again the Stokes line. So just see. I'll just explain why later. Now, so when the molecule is placed in electromagnetic or the photon is incident on the molecule, because of the interest, see the molecule is said to be polarized. That means the positive pole attracts the electrons, the negative pole attracts the nucleus. There will be a separation of the charge centers that induce dipole moment. So induced dipole moment is directly proportional to strength of the electric field of the electromagnetic radiation. So we know P is equal to alpha E, where alpha is the molecular polarizability. Now, so we know classical theory that everybody who studied all these things, just see. So when an electromagnetic radiation incident on the molecule, so where E is the E equal to E0, the electric field of the electromagnetic radiation can be explained in terms of either cosine or sine form. So sinusoidal form, we can say I can take a cosine form equal to E0 cos 2 pi E0 into T. Let Q be the normal coordinate associated with the particular mode of vibration frequency nu. Then we can just see that is P equal to alpha E, alpha equal to alpha E0 cos 2 pi nu0 T. For a small amplitude of vibration, so the polarizability alpha is a linear function of Q. The Q is a normal coordinate associated with the vibration. So alpha is a polarizability. It can be expressed in terms of Taylor series alpha equal to alpha 0, dou alpha by dou Q, Q0 at dot Q, etc. Just to give put on the values of 2, we'll get see the result to the three components. One is nu0 minus nu0 plus nu. There are three components. One is nu0 is the incident frequency. Nu0 nu minus nu, that is the frequency lower than the incident frequency. Nu0 is incident frequency. Nu0 minus nu is the frequency lower than the incident frequency, that is Stokes line. And frequency nu0 plus nu is the frequency greater than the incident frequency, that is anti-Stokes line. So for the classical theory, you can get the three components: same frequency, higher frequency, and lower frequency. But say it fails to explain the intensity. As you know, that you can see, just see. So there is a variation of the frequency. So that was not explained in the classical theory of Raman scattering. So classical theory predicts only there are three components: the same frequency, higher frequency, lower frequency. But it fails to explain the intensity of this line. But actual intensity is like this. That's why it just go to the quantum theory. So quantum theory clearly explains why the intensity variation occurs. So Stokes line, the Rayleigh line is high intensity. The intensity is the Stokes line lower than the Stokes line. Then anti-Stokes line, again the intensity is lower than Stokes line. See, so here V equal to 0, V equal to 1. Where V equal to 0 is the ground state vibration level. V equal to 1 is the excited vibration level. Now, so we know that the separation between the vibration level is of the order of 1000 to 4000 wave number, centimeter minus 1, some kilojoules of energy, some hundreds of joules of energy. So when the molecules in the ground state be equal to level, 0 level, so when an electromagnetic radiation is in the molecule, after absorption of energy, it goes to the virtual level. So that this level is a virtual level. that level, see, is virtual level is only a temporary level. It is not the stationary level. So that level varies from one molecule to another molecule. So that level depends on the energy of the incident radiation and the molecule. Suppose you are giving more energy, the level may be shifted more. If you give the more energy, it comes to lower level, this level. Okay. So this level depends on, okay, this level depends on the energy of the incident radiation and the molecule. So after absorption of energy, go to the virtual level. The only condition for the normal Raman scattering is the virtual level should be below the excited electronic level. The virtual level should be below the excited electronic level. That's the condition. So we can give the energy up to just below the excited electronic level. If it just matches or touches the excited electronic level, then the Raman will be resonance Raman. For normal Raman, the energy level, the virtual level energy level should be below the excited electronic level. Okay. So once the molecule absorption of energy, it goes to the virtual level and comes back to the first excited vibration level. That means the photon takes photon gives some energy to the molecule, or the molecule takes some energy from the photon. So here the frequency will be, the energy will be lower than the incident energy. So this is Stokes line. Whereas in the case of anti-Stokes line, it is originated from the V equal to 1 level. That is first excited vibration level. That means, so I told you, so V equal to 0 and V equal to 1. V equal to 0 is a ground vibration level. V equal to 1 is the first excited vibration level. So the separation between the vibration level is of the order of, say, around 1000 to 4000 Kelvin ampere. So the room temperature, the molecule attains energy. That is, that we just calculate the Boltzmann distribution. We can just calculate 3/2 kT. So that energy is not sufficient to go from V equal to 0 to V equal to 1 level. So only very small number of molecules will be in the excited level. Only maximum number of molecules in the ground level. So here V equal to 1 level, so after absorption it goes to the virtual level and comes back to the ground level. So here the photon takes some energy from the molecule, or the molecule gives some energy to the photon. This is again the inelastic scattering. So here the energy will be more than the original energy, incident energy. So therefore, see, this is originated from the ground level. This is originated from the first excited vibration. The population is maximum in the ground level. The population is very small in the excited level. So since the intensity depends on population, so Stokes lines are more intense than the anti-Stokes line. Okay. Now, we know that we just take the carbon dioxide molecule. So carbon dioxide molecule, this is the linear molecule. So there are 3n minus 5 normal modes of vibration. You can expect 4 normal modes of vibration. One is symmetry staging, the other one is asymmetry staging, the other two are bending. Since the bending modes are doubly degenerate, okay, doubly degenerates. The one more thing, just see in this equation, the classical theory equation. So see, if dou alpha by dou q is equal to 0, what will happen? So there is one equation, is one bracket is there. So if dou alpha by dou q equal to 0, these two terms will be 0. That means you get only u0 alone. You will not get u0 minus u. You will not get u0 plus u. So the condition for getting the Raman spectra is here. Just see, there should be a change in the polarizability, either in one component. Okay. So then only it will be Raman active. See, if dou alpha by dou q is 0, these two terms will be 0. So you will not get any Raman line. Only you will get exciting line. So for getting the Raman spectra, there should be dou alpha by dou q should not be equal to 0. There should be a change in polarizability. That is the condition for getting the Raman spectra. Just see here, the case of symmetry staging. So symmetry staging. So this is, normally the polarizability is ellipsoid. Just see the variation of pole stability with the displacement coordinate, you just see this varies like this. That is, dou alpha by dou q is so this dipole moment. Okay, dou mu by dou q is not equal to 0. This is the case for symmetry staging. So this is other two. Just see the case of bending mode. So there is, see, if this is dou mu by dou q or dou alpha by dou q, there is equal to 0. Again, asymmetry staging, this is dou alpha by dou q equal to 0. So the Raman, the condition for getting the Raman spectra is that it will be change in dipole moment. So change in polarization, sorry, change in polarization. So here you get only one Raman mode is active. That is, symmetry staging mode is active in Raman. All the other two modes are inactive. You know that. So our carbon dioxide molecule is a linear molecule. You can expect 3n minus 5 normal modes of vibrations. But so in that case, there is one symmetry staging, one asymmetry staging, two bending modes. Since the bending modes are doubly degenerate, that means two vibrations having the same frequency, you can expect only 3 bands. But out of 3, only one mode, that is symmetry staging mode, is active in Raman. All the other 2 are inactive in Raman. Okay. Then what is Raman scattering? So scattering of its light. Okay, so that I already explained all this. Now, so that is the Stokes, that is a quantum theory of Raman effect. So this is a ground excited electronic level. So this virtual level should be below the excited electronic level. Okay, now, so this is the Raman spectrometers. So any spectrometer, a source is required. So sample compartment, wavelength selector, detector. Okay, and record. These are the essential component, essential part of the spectrometer. So I told you that before the discovery of laser, this source is usually source a mercury source. So once after the discovery of laser, the source is usually a laser source. So that is the spectrometer is called laser Raman spectrometer. So this is a sample compartment. So sample compartment, any type of sample, any color sample, whatever you like, either solid or gas or liquid or any color, you can record the Raman spectra. Before that, the sample should be normally when you go through the olden days, you see that it should be transparent. It should be highly purity, highly so no black sample is not recorded Raman spectra. No, nowadays any color of sample, any phase, either solid phase or liquid phase or gaseous phase, you can record the Raman spectra. Then wavelength selector. So you can any wavelength, you can using the say CCD camera or anything, you can get the wavelength select, you can get it. Then detector, recorder, you can using this good Raman spectra. So earlier, if you use the dispersive Raman spectra, so you can take 4 to 5 hours for recording the Raman spectra. Nowadays, this Fourier transfer Raman spectra, you can just 3 to 1 to or 1 minute or 1 minute or 2 minutes is enough to record the Raman spectra. So that's why the number of spectra papers are coming day by day is enormously increasing. So because of the available sophisticated instrument available system, so large numbers of papers are publishing nowadays. Okay. Now I told you the hurdle it's a Fourier transform. So Michael's interferometer setup, they have just used this one. There is good Raman spectra, highly resolved Raman spectra. You know, Raman spectra very sharp line. So good resolved spectra, you can able to record. Earlier, the spectra will be broad because this. So in the dispersed system, so normally when you record here 5 to 6 hours or 7 hours, because of the system is heating, when chart record is moving fast, so sometimes the peak will become broader or sometimes become slow. So that type of problems will be there in olden days. Nowadays, there is no problem using a computer. So you can get the A4 size paper, you can get the spectra very easily, good spectra. Okay. In the case of liquid sample or gas, can see solids can be powder molecular sample can be sealed in a glass tube. Suppose the sample is a hygroscopic one, you can evacuate the sample and seal it. You can just record the Raman spectra. So there are all the samples you can record. So if it is in any gases, you can record. So just to fill the gas in the tube, just replace the sample holder, you can record the Raman spectra. So I told you any kind of sample, either solid or liquid or gas, you can record the sample very quickly. Now, it's a single crystal spectra. See, single crystal, you know that this is A-axis, B-axis, C-axis. You can just cut in any size. You can just pause the laser radiation either SI direction or B direction or C direction. You can just change using a polarimeter. Just you can change it. Okay, change the direction of the incident light and the direction of the scattered light. You can change the electric vector of the incident light and electric vector of scattered light. You can change it any direction. This is goniometer get. You can change it. A crystal can be cut in the parallelepiped, and you can just see find out the A, B, C axis. You can just pause the radiation in the X direction. You can scatter light. You can get the spectra in the Y direction, or you can get the direction, Z direction, or get the excited radiation in the X direction. You can change the direction of incident radiation and direction of scattered radiation. Okay. Normally, before that, one notation is there: X, Y, Y, Z. X is the direction of incident radiation, and the bracket Y, the first Y is electric vector of the incident radiation. The bracket second Y is electric vector of the scattered radiation. The second out bracket Y is that is the electric vector of the scattered radiation. So the direction of the scattered radiation. So in that way, you can change the direction of incident radiation, scattered radiation, so that you can be able to put the information from the single crystal, whether the mode is polarized or depolarized, that you can be able to get it from the single crystal. So single crystal is using the goniometer get, you can get the good information from the Raman spectra. And then I told you this is a the scattered radiation. You place the polarizer and the analyzer is parallel, then if the intensity is almost same, sometimes then it is a depolarized scattered radiation. If it is placed perpendicular, the intensity will be less. Okay, so the depolarization ratio, by using the depolarization ratio, we can able to find out the symmetric mode, whether it's symmetric or asymmetric mode, we can able to get it. So this will be used for single crystal spectra. So rho is a depolarization ratio, rho equal to intensity of light transmitted perpendicular to the intensity of light transmitted parallel. Now, see this, just see, so just record the one spectra and just change, variation changes. This will be, so the intensity will be same frequency without changing the wavelength frequency, the intensity will be changes. Just the polarizer and analyze the same parallel. So this is almost the intensity will be, whereas just to place in the perpendicular, key depolarized bands, it's almost the same frequency, whereas the symmetric mode, there is one band, one spectra, this the intensity like this, another spectra, the intensity like this. So the rho value, intensity of light transmitted perpendicular to the intensity of light transmitted parallel, is less than, in between 0 and 0.75, then it is totally symmetric. If it is equal to or greater than 0.75, then it's totally asymmetric. So whether the mode is symmetric or asymmetric, that we can obtain from the Raman spectra. Okay, so that you can able to the depolarization ratio, you can able to get it. Now, you know that is a vibration spectra. So information you can get it from the Raman spectra is, say, internal vibrations and external vibrations. Normally, internal vibration will be rich in the region 400 to 4000 region, or 300 to 4000 region. So below that, there is a external vibration. Sorry, external vibrations. There is translations and rotations. We know that this is internal vibrations, of stretching and bending or deformation. External is translations and rotations. See, in the case of Raman spectra, these low frequencies. Normally, we are discussing about the high frequency region, but most of the frequencies are response for the low frequencies. Most of the physical properties are comes to the low frequency region. So that is also important for us. So for a physicist, low frequency is also important. Most of the physical parameters are, say, in the case of, say, phase transition or the Dirac properties, all these comes to the low frequency region. So we are just ignoring only to find out the molecular identification, molecular groups. This 400 to 4000 wave number is enough. Or physics says, or physical property, most of the physical property comes in the low frequency region. So that is also important for us. So, you know, here you can record the Raman spectra from say 10 wave number to 4000 wave number. Okay, so if you use this high laser, high instrument, so nowadays this is recording about 50 wave number, 4000 wave number, no problem. Even there are instruments some high resolution instrument that is even can able to record the 10 centimeter was to say 4,000 wave number. So same detector is now. So depending on the say detector, so sensitivity, you can record the most one spectra you can get the four whole region. You just go to the AR spectra. So far IR different sensor, mid IR different sensor, say near IR different sensor. All these sensors are different required. But here the Raman spectra, so from 10 wave number to 4,000 wave number, only one instrument is enough to record the entire region. Okay. Now this is a stretching that everybody knows. You have studied all these things. This is symmetry stretching. Oh, okay. Now we know that normally, see, you can able to identify the modes. So what are the functional groups present in the molecule? So say different regions, there are characteristic frequency regions. So different group comes in a different region. So this is normally all the molecule gives him. There are occasions where the frequency is shifted. So once you get the thorough idea about this, then only you can able to assign correctly whether this is due to this, whether this particular vibration should hit this particular this group, so that you can able to identify it only by the expectations required. Okay. See, because of hydrogen bonding, now everybody knows the hydrogen bonding. So because of the hydrogen bonding, suppose this OH hydrogen bond go. So because of the strength of the hydrogen bonding, the stretching frequency decreases, bending frequency increases. So there is the stretching frequency will decrease and increase, the bending frequency will increase. Okay. So depending on the strength of the hydrogen bonding, there will be a slight shift the frequency. Okay. Okay. Hello, I'm audible. Hello. Hello.
Yes,
Hello.
sir. Yes.
Okay.
Yes.
Yes. Okay. Now see, we know that the vibrational frequency depends on the strength of the bond between the atoms and the reduced mass of the system. So we know that mu equal to 1 by 2 pi root of q, root 1 by 2 pi root of k by mu. K is a force constant. Force constant is the presence, the strength of the bond between the atoms. And mu is the reduced mass of the system. Suppose C single bond C, C double bond C, C triple bond C. So only thing is mass same, but the strength of the bond between the atoms of changes. So the frequency shifted. So strength increases, constant decreases, the frequency is also a high region. So for single bond, 1200 wave number, for C triple bond, 2200. Even though the mass is same, bond strength is different, the frequency is different. Whether it is isolated or conjugated or aromatic. So whatever the things. So based on the frequency, you can find out whether this is isolated, CW1C, or conjugated, CW1C, or aromatic. So from the frequency, you can able to identify. Okay. Then I told you, so alcohol, the OH, NH, normally OHO, NHO, this is a possibility of hydrogen bonding. So there will be a slight shift in the frequency. Then aldehyde, ketone, carboxylic acid, ester, amide, this type of, say, just see the frequencies usually come. Now, see, Raman spectra or Raman spectrometer is mainly used for certain specific purposes. So we just to identify the purity of the diamond, say that if you just use only one peak, 1332, that means that diamond is pure, highly pure. If there's any another peaks are there, that means it's impure. So identify to test the purity of the diamond. This is the only method to check the purity of the diamond, that is using Raman spectra. Then silicon, similarly silicon, germanium. So this type Raman spectra is similarly, there are so many pearls are available nowadays, whether it is original pearl or false pearl. There are so many pearls. People are cheating pearl. No, this is what they know. But if you just regard the Raman spectra without changing any, say, destroy anything. Okay, so this is non-destroy, so very non-destructive tools, no, without destructing any, no scratching, nothing. Just record the Raman spectra, place the sample in the Raman spectrometer, you'll get the spectra. So from the spectra, you can able to see this one is either whether this is a wood pearl or it's a fox pearl, that you can able to find out. then whether it is ivory or plastic. So there are so many people are cheating nowadays. It is ivory, but we don't know because our naked eye, it is very difficult to distinguish all these things. But we just regard to clearly say this is say ivory or this is plastic. So you can able to find out. So there are so many spectra are already there reported spectra. You know, Raman spectra of cholesterol. So there are some fingerprint regions are there, some signatures there. You can find out this is the spectra of cholesterol. Okay. Now this time just going to the spectra. Now this is the spectra of glucose, lactic acid, creatine, and say this is creatine, urea creatine. No? So spectra. It's a good spectra. Now she said this is a spectra for the phase transition. So there's some crystal triglycine sulfophosphate. So this I got report. I got published the paper Crystal Research Technology in 1994. So that's why I told this notation is called photon notation. So that is Z is the direction of the incident radiation. This X is the direction of the scattered radiation. This Y is the electric vector of the incident radiation. This Y is the electric vector of the scattered radiation. Okay, so just the same notation I recorded by changing the temperature. So the temperature decreases. So this first from starting from 300 Kelvin. So the intensity of this band, this decreases, and particular that this the intensity remains constant. So that is a transition temperature, phase transition. So once that's called softening of mode. So that is comes the say this is the low frequency region, or they say between around 80 wave number and 100 wave number. So in this region, you can able to whether the phase transition temperature or can be able to kind of phase. That means it's a solid state phase from one phase to another phase, not the liquid to say gas, not like that. It's a solid phase transition, solid state phase. So the order parameter change of the crystal. So from change from say one monoclinic to orthonomic, say different type of phase can change. So that can be determined from the Raman. By changing the temperature of this sample, you can able to find out the phase transition temperature. So the phase transition means the property of the crystal also changes. So that which temperature you can change. So the property that will stand to another method. So that you can able to find out. Now see, one of the hurdles of the Raman spectra, say this is a fluorescent spectra. If you just regard the Raman spectra, you can get this is say this is one compound, this is a spectra like this. So there is no information you can get it from this type of spectra. Just see, just like increases. So because of the fluorescence, you will not get the spectra. There is one hurdle of the Raman spectra. So in order to see this, if you just record the sample in the 514 point, there is a green light laser source, you will not get the any Raman spectra. If you just record the change in the laser line, instead of say 514.5 nanometer, we just change the laser line 785 nanometer. See, you'll get a good Raman spectra. Okay, so we can change the Raman spectra. Okay, by changing the incident frequency, say we use the 1064 or 785 infrared laser, you can reduce the fluorescence because the fluorescence can be reduced by changing the incident light of NER source. That is, since 1064 nanometer or 785 nanometer, you can avoid the fluorescence of the compound. Okay, now so after the discovery of Raman, there are so many developments are there. There is surface enhanced Raman spectra, resonance Raman spectra, angle dissolved Raman spectra, hyper Raman spectra, spontaneous Raman spectra, optical T-stage Raman spectroscopy, stimulated Raman spectroscopy, then spatially offset Raman spectroscopy, coherent anti-Stokes Raman spectroscopy, Raman optical activity, transmission Raman spectroscopy, inverse Raman spectroscopy, stiff enhanced Raman spectroscopy, surface plasma photon enhanced Raman scattering, stand of remote Raman, convocation Raman. There are so many spectroscopes after the discovery of normal Raman. See, there are so many Raman spectroscopy techniques are developed. Okay, say this is optical two-stage Raman spectroscopy. We use the Raman imaging. We can able to find out Raman imaging. Okay, so there are so many techniques are developed. Just I'll explain one or two. So in the case of say resonance Raman, what is the resonance Raman means? You can enhance even a small trace of compound about 10 to the power minus 6 to 10 to the power minus 8 molar concentration. You can get the good Raman spectra. Okay, so So the concentration is a very small, even a trace element. 10 to the power minus 6 means 10 to the power minus 8. See, this technique can be used for the sensors, a small, a trace quantity. So that can be detected using the resonance Raman spectra. Just see, so instead of the case of resonance Raman, instead of fundamental modes, you can just get the overtone and combination modes. Overtone means a fundamental is 1. So first overtone, 2 new 1, 3 new 1, 4 new 1, 5 new 1, 6 new 1, etc. So fundamentally we know that either from 0 to 1 transition. So overtone means first overtone means 0 to 2 transition. Second overtone means 0 to 3. So in that way, you can, in addition to the fundamental bands, you can guess the overtone bands also. So this is a resonance Raman spectra of the compounds. Say 4 in 2 compounds. Good Raman spectra. So see here, again this is a stimulated Raman scattering. This is actually a non-linear Raman. Now for recording the non-linear Raman, pulse laser is required. So that means, so that laser for the non-linear Raman means you have to give the power. So this almost equal to the electric field strength of the atoms like crystals. So here, if we record 10 to the power 9 volt per centimeter power, we just apply this one, we get in the molecule, we give non-linear. So non-linear Raman, then coherence anti-Stokes Raman. So here, you get normally Raman spectra will be nu1 minus nu2 or nu1 minus nu. But you can get the 4-way mixing method, you'll get the Stokes, anti-Stokes line also, nu0 plus nu. Suppose you are using a 2 laser here, one pump laser, the other one is probe laser. So pump laser keep on, one is fixed, the other one is vary. Suppose nu2 equal to nu1 minus nu2, that is nu1, nu2 equal to nu1 minus nu. Just doubt the scattering frequency will be nu1 plus nu. Normal Raman will be nu1 minus nu. The intensity will be more. But when the case of again coherence anti-Stokes Raman line, so in using the pump and probe laser by way of wave mixing method, you'll get the anti-Stokes line will be more intense. That is coherent anti-Stokes Raman spectra. Okay. Now this is a confocal Raman spectroscopy. See, even a small pinch of sample is enough. So record the Raman spectra. Even a cell, let's record the Raman spectra. Okay. So there's a field depth, all these things. Just record the using the confocal. Even if this is a pollen grain. So this is a spectra. Okay. Now, so mapping of drug tablet. So different thickness. Thickness, say the thickness drug books in evening, we just take the tablet. So there are coatings are there. So each coating you'll get a different spectra. If there is any unwanted elements, you can able to find out immediately from the spectra. So that will be useful for the Raman spectra. Say the drug layer, outer layer is polymer, then drug layer, different layer. So different thickness, you can get the Raman spectra. So if there is any unwanted elements are there, unwanted compounds, you can easily identify the spectra. Okay. Then tissue. See, this is a Raman spectral pathology of. Say this is a calcified this region. So normal artery, so plaque. So this over region, so different region, even in the Raman spectra. So there is collagen, eastern, actin. Then this is carotene, cholesterol. So they can expect the spectra. So in which part is there? So that you can able to get from the Raman spectra. So even think this is a red blood corpuscles, it's a Raman spectra. Okay. Then this is the image of this one. Raman blood cells imaging. See, nowadays, now it is used for clinical in vivo Raman system. So you can able to say small Raman system. So this is using a fiber Raman probe, just like an endoscopy. This instrument can be used to find out the, say, in any portion, just enter it, and you can able to find out using the Raman probe, just like an endoscopic technique. This is can be nowadays it is used for in Raman live cell imaging. So it is used for the clinical system. So in future days, just like say MRI imaging, this Raman imaging also more will be benefited for early detection of cancer. Research is going on. The next is so shall I go 5 minutes more? Dr. Veena?
Yes, sir. Yes, sir.
Okay. So see, Raman scattering, I told you, Raman scattering is a very, Raman signals are weak signals. Now, in order to enhance the Raman signals by about 10 to the power 5 to 10 to the power 6 times, the molecule is allowed to absorb some metals or either gold or silver or copper metals. So this is normally most of the types are silver and gold material, gold metals. So the enhancement becomes 10 to the power 5 to 10 to the power 6 times. So you can able to get this. The molecule is allowed. There are two methods. One is electromagnetic, and there are two mechanisms. One is electromagnetic enhancement mechanism. The other one is chemical enhancement mechanism. There are two mechanisms normally used for the Search spectra. Okay, so that is the molecule is allowed to absorb. This is normal Raman. So here is the molecule is allowed to absorb a metal. You will get a good signal. So the about the intensity 10 to the power 14 to 10 to the power 16 density. So the sample concentration is a very millimolar or micromolar, 10 to the power minus 3 to 10 to the power minus 6 molar ratio is enough. So when this technique can be used as a say sensors also, because a trace element can be detected using the Search spectra. Okay. Now, okay. So this is gold particle. So normally this is a gold particle is allowed to particle is allowed. That means the particle is sit over the surface of the color particle. The laser the enhancement is 10 to the power 6 to 10 to the power 14. Okay. So there are two theory. Now, this is the advantages: molecular fingerprinting, tagless biosensing, multiplex sensing, in vivo applicability, femtomolar and beyond. That is the concentration of the sample is femtomolar. That is very 50 molar. That is very concentration is very less. So that this technique can be used. So the just this one molecule record the Search spectra. This is spectra. This is the normal Raman spectra. This is a 10 spectra of 10 to the minus 5 molar, 10 to the minus 4 molar, 10 to the minus 5 molar, and 6 molar. Okay. So this is the molecule is allowed to absorb on the metal. Then it is just entered the cell because the whole particle is a nanoparticle. The size is about 10 to 20 or 25 or 40 max nanometer size. So thus molecules sit over the surface of the gold particle. So that easily into the cell. Then the molecule will interact with the any whatever the cells, either cancer or malignant cells that interact. So that will kill the cancer cells very easily. So this is the method of. So this Search spectra can be used for the say detection of cell surfaces. Or this techniques can be used for the cancer biomarker or for detection on cell surfaces, because the drug molecule is into the gold colloidal metal particles, metal cell surfaces. Then this, since the colloidal metal particle is very small size of the order of 10 to 14 nanometer, that can easily enter into the cell. So since the drug molecules sit over the metal surface, that will interact with the molecules. That will kill the cancer cells. So that will destroy the cells. Okay, so you can able to find out the normal cell and carcinoma cells. Okay, so that you can able to record the Raman spectra. So normal or malignants that you can able to detect using the Raman spectra. So there are so many these are going on. Sensitivity of NIR Search, near infrared source, using Search spectroscopy of different tissue depth. So they are depth even say 1 to 10 millimeters, 6 to 7 millimeters. So different spectra are noticed. So by injecting a cancer cell and just whether this how it is spreading like this, that you can able to find out using the Search spectra. Okay. So in vivo cancer targeting NIR Search spectroscopy, how it is targeted, how the say they are allowed to inject a cancer cell, then they are allowed to study the Raman spectra using Search spectra. Then they will find out how much it is say spread, how it is cell is increasing, whether it is tumor or so that you can able to find out from the Search spectra. Okay, so you can see yes. Nowadays it is called a chip enhanced. So that is mainly used for chemical imaging at a nano scale. Okay, chemical specificity of Raman spectroscopy imaging is spatial resolution typically about down to 10 nanometers. So nowadays, even so this technique can be demonstrated on various sample reaching from nanotubes to DNA molecules. Okay, so these techniques are developing nowadays. Chip enhanced Raman spectroscopy. Okay, with this I'm just conclude. Thank you for your attention. Thank you. Can I welcome your questions? Okay. Hello.
Yes, sir. Yes.
Hello.
It was such an enlightening speech. Thank you, sir.
Thank you.
Now, the session is open to questionnaire. You can either use your raise hand option or put your questions in the chat box. No questions? Thank you, sir. Next session starts at 12 o'clock.
Okay. Thank you. Thank you so much. Thank you.
Welcome back, everyone. It's my honor to invite Dr. Sunish Mathews to addressing the session. Dr. Sunish Mathews completed his PG from CMS College Kottayam under Mahatma Gandhi University. He qualified GATE and joined IIT Guwahati. He received his PhD from TU Dublin Institute of Technology, Ireland. He worked here as a research assistant for the development and optical characterization of novel organic dyes, phthalocyanins with high third-order optical nonlinearity. His doctoral research focused on fiber optic sensors based on photonic crystal fibers for electric field sensing. At Dublin, he has also worked as a postdoctoral researcher for the development of miniature fiber optic sensors to provide force feedback for handheld laparoscopic surgical instruments. He is currently a research assistant in the EPSRC Center of Interventional and Surgical Sciences at UCL. His research is focused on developing fiber optic sensors and probes for ultrasonic needle tracking, photoacoustic sensing, and intravascular imaging. His research interests are broadly in fiber optic sensors for minimally invasive surgery. Handing over the section to you, sir. Over to you, sir. Thank you.
Well, good afternoon, everyone. So can you all hear me and see my slides?
Yes, sir.
I suppose that is a yes. Okay, thank you. So firstly, let me thank the organizers of this conference and particularly the coordinator, Dr. Veena Rajesh, for inviting me to this conference. And it is a pleasure to present my work at this conference. So the topic that I'm going to present or talk about is fiber optic sensors in medical applications. So here is the outline of my talk. So I will briefly introduce the topic of fiber optic sensors to you all. Then I will briefly talk about fiber optic sensors that are used in minimally invasive surgery. And I will talk about a fiber optic ultrasound sensor that we developed in our research group, and also talk about how we put it to use in application, in two main applications in minimally invasive surgery, which is needle tracking and all optical intravascular imaging. So let me start by just briefly describing what are optical fibers. I suppose everybody here knows what are optical fibers and that they are mainly used in telecommunication. So optical fibers are basically long cylindrical optical waveguides that are used to transport optical energy and information. So on the right here, I have an image or a cross-section view of an optical fiber. And what you can see is that the fiber consists of a core and a cladding. So the core has a relatively higher refractive index compared to the cladding. And because the constituting material is made of silica, which is fragile, it will normally have a plastic coating covering it to protect the fiber. So depending on the difference in the refractive index, the fiber can be single mode meaning that it can just transmit light along one of its fundamental mode. And if the refractive index difference is larger, it can transmit many modes through it. So the light transmission mechanism through the fiber is through total internal reflection. So you put light in and the light gets trapped inside the core, suffers multiple reflections, and that's how the light transmission takes place. So the optical fiber is a highly established technology in telecommunications because of its low loss transmission, high information carrying capacity, and small and lightweight dimensions. So now let us look at what are the advantages of an optical fiber as a sensor. So these are the very general and important advantages that motivates researchers like us to find new applications for sensing using fiber optic sensors or fiber optics. So basically, the sensor or the fiber is made of dielectric material. So that means that it is non-electric and non-magnetic in nature. So this is a huge advantage when compared to electronic sensors or the conventional sensors, because it provides electromagnetic and radio frequency immunity. So, and this becomes a very big advantage for us who are trying to employ these fiber optics in minimally invasive surgery. The other advantage, of course, is small and lightweight. Basically, you can make really small and miniaturized sensors that can allow access to normally inaccessible areas. For example, the artery or veins inside the human body. The other advantages are it facilitates remote sensing, it is resistant to ionizing radiation, and it allows multi-point and distributed sensing. Basically, you can have many sensors sensing various parameters with just one system. So, for example, trying to look at the stress experienced by a very huge structure like a bridge, and so you can implant or integrate the sensor at many locations on the bridge and monitor the stress experienced by the bridge while the traffic is flowing over it. So that is a big advantage with fiber optic sensors. And given the robustness of fiber optics, it can function in very harsh and hazardous environments. So these are the basic or the generic advantages of optical fibers and the reason why researchers like us are interested in employing them in optical fiber sensing. So now here are the most basic components of an optical fiber sensor. So basically, to start with, you will have your sensor, which is basically a section of a optical fiber, which I call here as a transducer. So the transducer is interacting with the external parameter that you're trying to sense. So this parameter is causing a perturbation onto this transducer. And as a result of that, the light that is being transmitted through the fiber undergoes certain changes in its properties. So if you are able to detect these changes, then in a way you can detect or sense the parameter and calibrate your sensor so that you can measure, detect, or sense this parameter. So what are the components that you would require? So of course you would need an optical source, and then you would need a receiver to see the changes that are happening to the properties of the light as the parameter that you're trying to sense undergoes certain changes. So what are the optical sources that you can have? Normally you can use a laser or a light emitting diode. And then on the detector side, it could be a simple photo detector or an amplifier system. So once you have all these, you can build up a optical sensing system. Now let's look at what are the properties that undergoes change when this external parameter is changing around this sensor. So the amplitude of the light can change. So if you can detect the change in the amplitude, you can relate it back to the parameter, the change in the parameter that is causing that, or the parameter that you're trying to sense. It can cause a change in the phase. It can cause a change in the polarization of the light that is passing through the fiber. There could be change in wavelength, shift in the wavelength. There could be change in the frequency of the light. And also there could be spectroscopic changes. So you can put a broadband light source and observe the spectroscopic changes when the external parameter is undergoing change. So this is the basic components of sensor and light modulation, and the way that you can build up a sensor by detecting the changes of the properties of the light as the parameter that you're sensing is undergoing a change. Now, these are the two main classes of optical fibers. So the fiber itself, is sensitive to certain parameters such as strain, such as temperature or refractive index. So when the fiber is, the parameter that you're trying to sense is directly sensed by the fiber, you call it as an intrinsic sensor. So the fiber itself is sensitive to this parameter. But then you get very high sensitivity because the fiber is sensitive, but at the same time, it is only sensitive to certain parameters. And to build up a sensor for your parameter, you may have to build up something called an extrinsic fiber optic sensor. So basically, to do that, you have to make changes at the fiber, or introduce, for example, a coating on the fiber, so that it allows you to it allows you to measure the changes that the parameter is undergoing. For example, it could be if you're trying to sense a molecule or a biomedical parameter, let's say. So that biomedical parameter will change some properties of the coating, and that coating will in turn induce a stress or a strain or change in temperature, which you can sense using the fiber optic sensor that you have. So there are intrinsic and extrinsic sensor. And at the same time, what I want to also point out that this is a different kind of configuration where the sensor is an endpoint sensor, where the sensing element is right at the distal end. And these are the sensors that we normally develop and use. So in terms of topology, there are different types of sensors that you can develop. Just as I was mentioning, this is a single point sensor. Basically, you have the sensor right at the end of the fiber. So you are looking at the properties that are changing on the reflected light that you're getting back from the end of the fiber. As I explained, you could have a multi-point sensor. So you can have a sensor at various locations or various points on this fiber. And it could be sensing your parameter at multiple locations along the length of the fiber. Then you can have a distributed sensor in the sense that the whole fiber itself is a continuous sensing element. So this is used in sensing strain or stress experience in bridge, for example. So the one fiber is used to stress strain at various parts. So basically, when the bridge undergoes a strain, it causes a change in reflection, and that you can detect using your detection system and monitor that the part of the bridge is undergoing a strain. So these are the different topologies of employing a fiber optic sensor, but I will be talking more about a single point sensor. Now, when there is a talk about fiber optic sensors, you can't skip this part. So fiber Bragg ratings are the most popular sensors so far. So how are fiber Bragg gratings made? So fiber Bragg gratings are made by causing refractive index modulation inside the core. So you apply a strong CO2 laser and cause refractive index modulation. So these black points and the white points are bars are the points where the refractive index has gone a slight modulation. As a result, when you put light into it, you get a strong reflection from a very narrow part of the spectrum. So that is the property of the Bragg grating. And this kind of sensor is very sensitive to changes in strain or temperature. So when the temperature changes or the pressure changes, there is a shift in this reflected Bragg wavelength. And if you can detect this change in the Bragg wavelength, and you can calibrate your sensor to the pressure or the strain that is causing this wavelength shift. So here is just an example of how you build up a fiber optic sensing system using a fiber Bragg grating. Basically, you will have a broadband light source, and then you are looking at the reflection spectrum. So when the strain is induced, the spectrum undergoes a change, and then if you can calculate this change and then also monitor the strain externally, you can then calibrate your sensor so that it is being able to measure these changes. So it's a simple system which you can use to build up a sensor for strain or temperature. And these sensors are very popular, and they have been used in many application areas. And we also have commercialized systems available with these sensors. To summarize this first part, let me just give you an overview of the application areas where the sensors have been used. So mostly they have been used in structural health monitoring, as I was saying, monitoring of stress in bridge, dam, heritage site, wind turbines, avionic structures. For example, the flights where these sensors have been installed on the wings of flights to monitor the stress and strain as the helicopter or the plane flies. And there is sensors being employed in oil and gas monitoring for pressure, temperature, and acoustic sensor. You can also monitor, they've been also been used to do pipeline monitoring. There are sensors used to detect electric field, magnetic, and current sensing. And then there are a huge range of fiber optic sensors used as biosensors for detecting cells, proteins, and DNA. And mainly the area that we are interested is in fiber optic sensors in surgery, diagnostics, and imaging inside the human body. So let's move on to the application areas. So this is just to give you all an overview of where fiber optic sensors have been used so far or researched into in biomedical applications inside the human body. So basically, there are many parts of the body or surgical procedures where these sensors have been used or utilized. So most popular, as I was explaining, is the FBG sensor. So the Fiberglass grating sensor. So FBG sensors can detect pressure. So they've been used in the brain to measure intracranial pressure. They've been used to do robotic eye surgery. Basically, sometimes robots are used to perform certain eye surgeries, and the FBGs can measure the pressure or the force that these robots are employing to do the surgery. So that way you can use an FPG to actually assist the surgery. A major part of fiber optic sensors is in the intravascular surgery, basically where you have heart problems or heart disease where the artery is blocked. So you can use a pressure sensor inside the artery to measure the difference in the pressure at the location of the block. Then the sensors are sometimes also used in thermal ablation. So when you have cancer, the common diagnostics is the common therapy is to thermally ablate that region. So you can monitor the ablation process of that region using a fiber optic sensor. And including that, there are many other application areas where the fiber optic sensors has been used or studied or demonstrated, and it's a very active area of research. And you can find these details in this reference that I have cited here. Now let me move on to the fiber optic sensor that we have developed in our group. So it's basically a sensor based on a Fabry-Perot interferometer. So the Fabry-Perot interferometer is actually built using a cavity. So you have two mirrors, and between the two mirrors, you have a polymer spacer. So this sensor we build on the end of a fiber optic cable, actually. So we use a single mode fiber, and then we perform multiple thin film coatings on this fiber. So we deposit the first mirror, we deposit the spacer, and we deposit the mirror so that a interferometer forms right at the distal end of this fiber. So when the ultrasound waves, they impinge on this cavity, it modulates the thickness of the spacer element. And because the thickness is modulated, the light that is coming into the cavity is reflected back. It causes a phase shift. So when you're looking at the reflected light, it modulates the intensity of the reflected light. So this is how the sensor works. The ultrasound waves causes a modulation in thickness, which in turn causes a modulation of intensity of the reflected light, which we can detect. And that is the basis of our fiber optic ultrasound sensor. Now, so with this kind of sensor, initially we had a problem, or we had an issue. Hello. Okay, so I can hear some interference. Sorry. So in this sensor, there is a, so as I was explaining, so these mirrors are planar. When these mirrors are planar, what happens is that the light, when it gets into the cavity, diverges. And when it diverges, it's called a beam walk-off problem. So as it undergoes multiple reflection, during each reflection, the beam is expanding and it walks out of the cavity. As a result, the amount of light that is reflected back into the cavity is very less, and you lose some of the optical sensitivity of the sensor. So in order to improve on this, one of my colleagues who had a brilliant idea, and he changed the shape of the cavity such that he made the other end of the cavity like a plano-concave cavity. So in this case, the spherical shape of the cavity focuses the light back into the core, and then you improve on the sensitivity. So there is no more beam walk-off problem. So this is a paper published in Nature Photonics by my colleagues. And just to show you the difference in the sensitivity. So what I'm showing here is a plot of the interference transfer function. So you put light into it, and when you're looking at the reflection, you get these interference pattern. Now, when the cavity is planar, as we had before, you can see that the interference transfer function is very shallow here. And if you take the derivative, it will be not as sensitive as the micro resonator or the plano-concave sensor, which has a sharp interference pattern. So you improve a lot on the optical sensitivity by making the cavity planar. So, and after we have fabricated a sensor, one of the important things that we do is to measure the frequency response. So you need to know what are the ultrasound frequencies to which the sensor is responsive. So we measure the frequency response. So here I show the frequency response of a particular sensor. So you can see that it is sensitive to megahertz ultrasound frequencies. And this is very important because this frequency band is used in clinical practice for diagnostic ultrasound. So very shortly, I will be talking to you about diagnostic ultrasound or ultrasound imaging. So these frequencies are used in the clinical practice for, and because our sensor is responsive to these frequencies, it can be used to measure ultrasound frequencies in this range. So this is where the main motivation of our applications comes from. Okay, so before I move on to the application area, I have to give you some background of ultrasound imaging. So the ultrasound imaging, as some of you might be aware, is used to image inside the body, actually. So it is an ultrasound system that looks like something like this, and it uses high frequency sound waves to view inside the body. So some of you may have had experience if you are a parent where you have gone to the hospital to and the nurse or the surgeon must have tried to view the baby that is developing inside the body of the mother, actually. So it's a normal routine clinical system that is used for examining the fetus. So it's a real-time imaging system. And the images are developed or formed by putting inside ultrasound waves into the body. And when the structures inside the body reflect back these ultrasound waves, you can form the images and see it on the monitor of the ultrasound imaging system. So here is just a photograph showing. So there is a mother with a baby inside her body. And this is the ultrasound probe. So this probe is actually an electronic probe, which is transmitting ultrasound waves and also receiving the reflections from the structure inside the body. And when that happens, you can see real-time images of the structure inside the body. So at this point, this nurse is pointing probably to the baby inside the body. So that is the ultrasound imaging system. So ultrasound imaging system is also used in surgery. So there are specific surgical procedures where a needle is inserted inside the body, for example, to retrieve a sample from the specific part of the body, to retrieve a sample for a further examination, or to inject fluid into the body. So some of the examples are cancer biopsy, where you put a needle inside the target area and get a sample out of it for further examination. The other is regional anesthesia. And then for certain fetal procedures, for example, to understand or look at the abnormalities in the fetus, sometimes you put a needle inside the fetus, inside the stomach of the mother, and take a sample out for a further examination. And then also for cardiovascular surgery, needles are used. And for all these procedures, the procedure is sometimes guided by ultrasound imaging. So when you look at the ultrasound imaging, you can see the images, the structure inside the body along with the needle. So it is important to view the needle so that you're not causing any harm to the other organs or the structures inside the body. So ultrasound imaging is sometimes used to guide these surgical procedures. So when the needle is inserted, the surgeon will look at this ultrasound image so that they can view both the structures together with the needle. So here is an example of an ultrasound image where the procedure of cyst aspiration. So there is a cyst, and a needle, which you can see here, has been inserted to take out a sample. So this is how roughly the needle looks like. And you can see also the cyst in using the ultrasound imaging. But most of the time, so the problem with the ultrasound guided procedures, needle insertions, is that the visualization of the needle can be poor, really poor sometimes. So it can be poor when you're using very thin needles. For example, in fetal surgery, very thin needles are used. So the image of the needle is formed by the reflection of the ultrasound waves that are reflected from the shaft of the needle. So if you're using a thin needle or you're using a steep insertion angle, sometimes the reflection may not reach back to the ultrasound probe. And as a result, you don't see the needle. And this can be very risky in an ultrasound guided procedure, because particularly if you're doing a fetal, if you're doing insertion into the fetus, you might damage the parts of the body of the mother, or even, the fetus inside the body of the mother. So just to show you here an example, so this is a documented procedure where the surgeon is trying to view the fetus and doing a needle procedure. So that is the fetal head, and the needle is in there, but it is supposed to be somewhere here, but it can't be seen. So what happened here is that when the needle was inserted, it moved out of the imaging plane and then became obscure and invisible. So the surgeon tried to move. So here is the video where I'm showing you. The surgeon is trying to move the plane, and after a time, the needle becomes visible here. So there is the needle. So these things do happen in these kind of surgery where you lost track of the needle. So you don't know where the needle is. And as you can see, it is very close to the fetus. And this is a very dangerous situation which needs to be avoided. So this is why there is research being done into improving the visualization of needle in these kind of procedures. And that is where I will talk about the first application of our ultrasound sensor, which is the ultrasound needle tracking. So the motivation of this technique is to improve the visualization of the needle tip. And how we do it is by integrating the ultrasound sensor right at the needle tip. So just to give you an overview, so you would have, normally you would have the ultrasound imaging system with its ultrasound transducer interacting with the patient and the needle. And then in this system, we introduce our fiber optic ultrasound sensor. So the needle is integrated with a fiber optic ultrasound sensor, and we have a separate tracking console or a tracking system that will allow us to track the position of the needle tip. So this system is acquiring signals from this hydrophone or the fiber optic sensor that is integrated in the needle, and the system will process these signals and then form an image of the needle tip, and that image of the needle tip is used to calculate the location of the needle tip with respect to the ultrasound image. So what the system is actually doing is also taking out these images. So it will take out the images from the ultrasound system, and on a separate monitor will show the ultrasound images together with the tracked position of the needle tip as a plus sign. So the modification that we are doing here is not very trivial. So first we integrate the sensor into the needle, and then the sensor is then being able to track the position of the needle tip. So here is how it does it. So when we look at the closer view of this, basically the ultrasound sensor that is inside the needle is receiving these ultrasound transmissions from the transducer probe. And when it receives, it helps to form the image of the needle tip. And as I was explaining, from this image of the needle tip, you calculate the position and then overlay it on the ultrasound images. And this is how a common needle looks like. So on the top here is a commercial needle that is normally used for these procedures, and it comes with a stylet. So the stylet is there so that it can block the needle while you're inserting the needle into the body, so that the unwanted fluids or blood doesn't get into the cannula of the needle. So the stylet is there when you're doing the procedure. So at the time of the procedure, when you have reached the target, you remove the stylet and then you do the procedure. So what we have done is that instead of using this commercial stylet, we made our own custom-made stylet with the fiber optic ultrasound sensor integrated into it. So that is how we integrate the sensor into the needle. And just to show you a microscopic image of the needle. So there is the needle, and this is the stylet, and that is the ultrasound, fiber optic ultrasound sensor right at the tip of the needle. Now, to show you how everything works here. So this is a video of a real-time needle tracking system. So before I show you the video, let me explain to you what is happening inside this video. So this video was, or the data for this video was recorded during an in vivo experiment on an animal, actually a swine or a pig. So when you have a system, when you have developed a system which you think is useful in a clinical practice or a clinical surgical procedure, so one of the steps that you normally do is to perform experiments on animals like rat or swine or rabbit. And we were very opportune to get this system to move into a surgical stage and perform this experiment. So what I'm going to show you here, when the video runs, you will see the ultrasound image of the thigh region of the swine. And the surgeon will be inserting a needle into the thigh region. And here is the artery of the artery of the swine, or it is called the femoral artery, which leads all the way to the heart of the pig. So the femoral artery is also there in the human body, and it is one of the access points to gain access into the heart. So the idea here is that the surgeon inserts the needle, and the target here is the artery, to gain access into the artery. So when the video runs, you will see that the needle moves into this artery, towards this artery. But on the right here, on the left here, sorry, you will see the image of the needle tip. So these are the signals that are being acquired real time from the ultrasound sensor that is inside the needle. So the spot you'll see here is a signal from the ultrasound sensor. And from this needle tip image, we take out a region of interest to perform some signal processing to improve the accuracy of the tracking. So you will, when the video runs, you will see everything together working frame by frame. So let me start the video. So as you can see, the needle is inserted and the position of the needle is indicated by this green plus sign. So at some point, you see that the needle has gone. You can't see the needle anymore. But with the tracking on and with the position of the shown by this ultrasound sensor, you can the surgeon can still know where the needle is actually. So this is our first demonstration of in vivo experiment using one of our sensors. So now moving on to the next application area. So before that, again, a bit of introduction to intravascular imaging, what it is, why is it used for? So the intravascular imaging is done so that you can, detect, for example, people with heart disease develop blocks inside their arteries. So there is buildup of plaque inside the artery. So just as I was explaining, the access is gained through the thigh region into the femoral artery, and the catheter or the probe that is used is, guided into the heart region, so that to the region of the block to perform imaging on this plaque, so that you can, so the surgeon can understand the extent of the plaque, how big it is, and what kind of therapy is required to, remove the block or, widen the artery so that the blood flow is normal. So here is an example of a fiber optic probe that you would use to do imaging. So this is an optical coherence tomography probe, and we use this probe for a different application, which I will explain in a short while. So that is a bit of introduction. So yeah, so the purpose of intravascular imaging is to assist in coronary interventions. Coronary interventions being heart surgery and visualizing the plaque. So basically, the purpose is to view the plaque, to determine where it is located, what is its size, and length. And once you have visualized this, the surgeon will make his choices based on whether a stent needs to be implanted in the arteries to widen it so that the blood flow can take place. So that is why you would use intravascular imaging. So there are two main techniques that are used for intravascular imaging. One is optical coherence tomography, and I showed you the probe in the previous slide. So the intravascular tomography is done using a fiber optic probe. Basically, it's done by light transfer, and you're receiving the reflected signal, and that helps you form an image. So here is the OCT, or the optical coherence tomography, inside the artery actually. So you can see the walls of the vessel here. And this kind of technique provides very high spatial resolution, so you can see clearly. But then at the same time, the imaging depth is not very good. So you get 1 to 2 millimeter imaging depth. And when you're trying to do intravascular imaging, it is important to visualize the plaque deposits. But the disadvantages of this system is that it does not give you any specific contrast for the plaque. So you can see everything, but you can't clearly distinguish the plaque region. So it does not provide any specific contrast to plaque. The other technique is intravascular ultrasound, which is similar to ultrasound imaging. So you put a probe inside the artery. So instead of light, you're using ultrasound to visualize the artery. So as you can see, the resolution is poor, but then one advantage is that you can see much more deeper inside the tissue. But again, this structure, this technique also has the same problem with no specific contrast for lipids. So these are the two state-of-art techniques that are being used for intravascular imaging, but they do have the problem that they don't have any direct lipid contrast, so you can't view the plaque very clearly. So to view the plaque, so we developed something called photoacoustic imaging. Now, photoacoustic imaging is a technique that is used in to image inside the body. And I have to again explain to you a little bit of this background. So what happens in photoacoustic imaging, it works on the effect of photoacoustic effect. Basically, you put light into the target area and the target absorbs this light, and while thermal relaxation, it emits ultrasound waves which you can detect to form an image of the target area. So what we are doing here is we are using the same optical coherence tomography probe. So there are two parts for it. So one is to deliver the excitation light to generate the photoacoustic waves. So first you deliver the excitation light, and using the fiber optic ultrasound sensor that I just explained a few moments ago, we detect the ultrasound signals or the photoacoustic waves that are generated. And this helps to form an image or a photoacoustic image inside the artery. So if you have target, so one advantage or one big advantage of this is that you can get specific spectroscopic contrast for target, provided that you use the right wavelength. So if you use the right wavelength at which the lipid inside the plaque is absorbing, you can generate photoacoustic waves from only the lipid region, and then you can clearly visualize the plaque area. So this is the idea of using intravascular photoacoustic imaging. And you can achieve image up to 4 millimeter depth. So how did we implement this is using a, so this is the actual image of our intravascular photoacoustic probe. So as I was showing you, so this is the optical coherence tomography probe, and which is paired with another fiber optic sensor here. So the light which we deliver through this optical tomography catheter will then deflect onto the target. The target will absorb, generate photoacoustic wave, which is detected by the sensor, and then that helps to form a circumferential image of the artery. So we are using here a commercial OCT catheter, and then we are using our own fiber optic ultrasound sensor. Now, let me show you some of the images here. So to test our fiber optic probe, we did something called, we did try to image a coronary stent. So this is the image of a coronary stent that is actually implanted inside the artery near the block region to make it wider so that the blood flow is normal. So, and these are all part of the surgery. So basically, we just use this to test our imaging probe, how well it can image inside the artery, or just to have a imaging target. So it is circumferential or circular in shape. So we put our probe inside somewhere around this region, and we did a circular imaging. And let me show you the image here. So as you can see, so that is the image that we are getting from this stent. So the probe is somewhere here, and then the ultrasound sensor is on this side. So you get bright images or bright images from these parts of the stent, whereas you still get some of the region where the OCT probe is blocking the ultrasound sensor. So you get 360, nearly 360-degree circumferential imaging with this system. So this is just to test our probe that it works and it can provide circumferential photoacoustic imaging. So the light from the OCT probe falls on the strut, which generates photoacoustic wave, and that is detected by our ultrasound sensor. And to demonstrate that it can actually work in a in an artery, we built a artery phantom. So this is how the artery or a vein phantom looks like. Basically, this is the lumen, and we will put our probe inside it. And this phantom was built to actually show that we can get specific spectroscopic contrast. So if you are using the right wavelength, you can excite a specific chromophore inside the body or inside the artery. So to simulate the chromophore, we put two tubes with certain dyes inside the tube. So one of them is methylene blue and the black is India ink actually. And then we use two separate wavelengths so that when you put one wavelength, it will excite one of the dyes. And when you put the other wavelength, it will excite the other wavelength. So by using a specific choice of the wavelength to excite the photoacoustic waves, you can excite a certain target area just to visualize it so that you can get complementary information together with the optical coherence tomography and the intravascular ultrasound. So that is the idea that we are trying to show here. So let me show you how the optical coherence tomography image. So when you look at the optical coherence tomography, it is everywhere. So you can see the vessel wall and the tubes, and you can see some contrast, which shouldn't be there, but it's there because the India ink is strongly absorbing. But if in the actual scenario, if it was a plaque, you will only see a shadow. You won't see the plaque very clearly. So this is the idea. So when you use photoacoustic imaging, so let me show you the photoacoustic image of this. So now what you're seeing is the signal only from the tubes from where the photoacoustic signal is being generated. So and on the top of the tube, so there are two tubes as I was explaining. The top tube has methylene blue. So in this case, we have used a wavelength that will excite the methylene blue. So you're getting a stronger signal from the tube from the methylene blue, whereas a weaker signal from the India ink. And if we were to use the wavelength at which the India ink is absorbing highly, you will get a stronger contrast from the tube with the India ink. So the idea is that you use the right wavelength, you can excite specific chromophores inside the body to particularly to image them. And as photoacoustic image just by itself is not a useful tool. So I have to let you know that it is a complementary imaging tool. So you have to use it with the imaging modalities like OCT or intravascular imaging to get complementary imaging. And what we are trying to build is a dual modality imaging system here. So with that, let me summarize. So I hope I have given you a brief introduction on optical fiber sensors. I know that I have explained things in very briefly and quickly without going into much of the details, but this is to give you an overall idea. So also I've explained or introduced our fiber optic ultrasound sensor with many application areas in minimally invasive surgery. And also given you an overview of how we use this sensor for ultrasonic needle tracking and intravascular imaging, which are very important in minimally invasive surgery. So with that, I come to the end of my talk. Thank you all for your attention. And if you have any questions or feedback, please feel free to do so. Thank you.
It was such an informative session. Thank you, sir. Now the session is open to questionnaire. You can either use the raise hand option or put your questions in the chat box. Since there are no queries, thank you, sir, for spending your valuable time with us. Our next session is paper presentation. There is a delay of 5 minutes. Please stay tuned.
Okay, thank you very much.
Since there are no queries,
the thin blue line of the atmosphere, the curve of the horizon, and that's when it became real. Really, at a gut level, I'm actually in space. We are on orbit. This is not a sim.
This is my eyes looking through glass at Earth from space. It was almost overwhelming.
And so I think it's kind of overload for your brain and processing all of that at once because it just isn't used to that.
You know, it's really hard to describe something like that because it's not just cerebral, it's emotional, it's kind of all encompassing.
The thin blue line of the atmosphere, the curve
my heart was
of the
racing.
horizon,
You couldn't
that's when it
smile
became
off
real.
of my face. It
really,
was
at a
really
gut
amazing.
level, I'm actually in space. We are on orbit. This is not a sim.